This is a Chase Bliss Clean pedal. It was originally called a dynamic enhancer before they started calling it a creative compressor. Clean is a compressor, and a very nice one, but it's also more than that, and it's changing the way I make music in a way that I find interesting. I think that compression is its how, but not its what or its why, and this video is my attempt to explain and demonstrate that idea. First, before I get into all that, I do think it will be helpful to understand what compressors are and how they work. Quick aside. During this video, I'm going to talk about a lot of stuff that's not directly related to this particular pedal. You might be asking yourself, why is this guy talking about this in this video that is supposed to be about a clean pedal? Well, as I mentioned in my prior video about the Chase Bliss Thermi pedal, last year Chase Bliss had a mystery box promotion where they did an end-of-year sale where you bought a pedal from them at a reduced price, but you didn't know what pedal you were going to get. I told myself when I bought a mystery box that I would make an instructional video about the pedal in the box no matter what it was. What was in my mystery box was a clean. I need to admit to you that I felt very unqualified to talk knowledgeably about compression. I have been recording music for a very long time, and of course I have been using compression that entire time, but it's always basically been like, turn the knobs until it's doing something and sounds better. So then I go and take a tutorial on YouTube, and it's always like, the secret to good compression is that you turn it down until it's not doing anything, and I get confused and I go back to turning knobs and not knowing the quote-unquote right way to use compression. So when I decided to honor my commitment to making this video, I kind of ended up in order to explain this compressor pedal, you must first explain the universe situation, where I was really doing a lot of research down to the bedrock of what compressors are about. Some of that was probably unnecessary, but I found it interesting and fun, so maybe you'll find it interesting too. I'll put in some chapter markers so you can skip the background if you want. And I want to preface all this stuff with the caveat that I am an amateur musician that works at a software company. I am not an electrical engineer or an audio engineer, so if I get any of this stuff egregiously wrong, please feel free to put corrections into the comments. Okay, let's start with a history lesson. Let's jump back to the beginning of the 20th century, right back to the invention of radio. The earliest successful radio broadcasts use a technique called amplitude modulation. Amplitude modulation works as follows. A transmitter uses an antenna to broadcast a sine wave at a very high frequency, high above the limit of human hearing. The transmitter can use an electrical current to destabilize the amplitude of that sine wave. That electrical current can be generated by an audio signal, such as one generated by a microphone. On the receiving end, there is another antenna attached to what we can call a demodulator, which is set up to pick up that high-frequency sine wave. And if it detects that the amplitude of that sine wave is changing over time, it takes those changes and turns them back into an audio signal, which can be played back through a loudspeaker. This arrangement is what we refer to as AM radio, which is a name that most of us have heard of, even if we didn't understand the mechanism by which it gets transmitted. This amplitude modulation situation is a bit precarious, though. If the audio signal that modulates the sine wave is too quiet, then the resulting changes to the sine wave won't be obvious enough to stand out against background noise. If the audio signal that modulates the sine wave is too loud, then that reshapes the sine wave to the point that the demodulator can't decode it properly, which results in distortion. So there's a sweet spot, a Goldilocks amplitude range that is neither too quiet nor too loud, and AM radio broadcasts need audio to stay within that range to work properly. What we need then is some kind of device that compresses the dynamic range of an audio signal. Enter the vacuum tube. Vacuum tubes were used in all sorts of electronics in the first half of the 20th century. Here's a real short, possibly incorrect, explanation of how vacuum tubes work. There's a little piece of metal inside a vacuum-sealed enclosure, usually a tube of glass. The little piece of metal, which is called a cathode, is made of some kind of conductive metal, which means that it has a bunch of free electrons held inside its surface that are in balance at room temperature. If you superheat that piece of conductive metal, the electrons get excited enough that they reach escape velocity and leave the piece of metal. The electrons escape into the vacuum of space inside the tube, and on the opposite side of the vacuum, there's another piece of metal called an anode, which is set up to attract electrons. There's typically also one or more elements called control grids that are placed between the cathode and the anode, which control the movement of the electrons across the vacuum. And those control grids can increase or decrease the amount of electrons that get from the cathode to the anode. In this way, you can use a vacuum tube to amplify and control electric current, and that is how tube amps work. So, back to the problem of AM radio, how can we use tubes to solve the issue that signals can be too soft or too loud for AM to work properly? The answer is that a peak detector in the circuit creates a control voltage that affects the control grid in the tube. The louder the peak in the audio in the system, the more the control grid gets turned down. There's a selectable DC bias that is combined with the control signal that allows users to control the intensity of this effect. This results in the Goldilocks situation we were originally hoping for. Loud stuff is made quieter while quiet stuff remains the same. Because you can control the intensity by controlling that DC bias, this is sometimes called variable bias compression. This is also referred to as variable mu compression, with the word mu being an engineering word for gain. So variable mu, aka tube compression, is the first kind of compression that was introduced. Clean is not a tube compressor. Tube compressors were followed in the 1950s by the introduction of the optical compressor. These work in a way that's a little different from tube compressors. Instead of the control signal affecting the control grid on a tube, it instead powers a tiny light inside the device, which changes its brightness depending on the control voltage. That light is adjacent to what's called a light-dependent resistor, which changes its resistance depending on how much light is hitting it. That change in resistance changes how much audio is processed through the circuit. The chemical reaction that changes the resistance is not instantaneous, and that gives optical compressors a characteristic slow response time that makes them particularly good for smoothing out sounds that don't have quick transients, such as vocals. Now, if you're either a person that's seen my video about the Chase Bliss Thermi pedal or somebody that knows about electronics generally, you're going to recognize this arrangement. This is sometimes called a Vactrol, and it is the reason you can't buy Thermis outside the US anymore. Light-dependent resistors historically have used cadmium as the magic chemical that changes its resistance based on light, and in the European Union, cadmium is not supposed to be used in consumer electronics anymore. So, at least in theory, optical compressors aren't supposed to be sold in Europe, and maybe also in California? In practice, it seems like it is still possible to sell and buy these things wherever though, so I don't know. Anyways, Clean is not an optical compressor. After optical compressors came transistor-based compressors. Transistors were designed to be a smaller, more stable, and more economical replacement for vacuum tubes. They're built using semiconductors, which are a type of material that is less conductive than a conductive metal, but still more conductive than an insulator, and can have properties that allow their conductivity to change based on some condition. Early transistor-based compressors used what are called field effect transistors, which are still a very common form of transistor. Field effect transistors, or FETs, have three elements called a source, a drain, and a gate. Applying voltage at the gate changes the amount of electrons that can pass from the source to the drain. When you look at it like this, you can see a sort of family similarity with the thermionic tube. The source is kind of like a cathode, the drain is kind of like an anode, and the gate is used like a tube's control grid. If you use a field effect transistor in place of a tube in a compressor circuit, that is what is referred to as a FET compressor. The first FET compressor on the market was the UREI 1176 compressor. These are still made by Universal Audio and still cost like $3,000 brand new. It's one of the most famous premium compressors in history. Clean is not a FET compressor. Okay, so we know it's not a tube compressor, it's not an optical compressor, and it's not a FET compressor. So what is it? Clean is what's called a VCA compressor. VCA stands for Voltage Controlled Amplifier, and if you're familiar with synthesizers, we are talking about the same component that changes the volume of a synthesizer sound. Essentially what happens in a VCA compressor is, rather than relying on the physical characteristics of some component to do the gain reduction, which colors the sound, VCA compressors are just designed to analyze the loudness of the incoming sound and turn down the amplifier based on how loud it is. To me, it's the most conceptually straightforward type of compressor we've looked into yet. The thing was, the integrated circuits to do this kind of amplification didn't exist until the 1970s. The first commercially available VCA compressor was the DBX 160, which aimed to do what variable mu compressors do but at a fraction of the cost. That came out in 1976. Which brings us back to Clean. We've established what a compressor is. It's a device that is used to keep an audio signal inside a dynamic range, and we described at a high level how different kinds of compressors do that work. We've asserted that Clean is a VCA compressor, which means it uses an amplifier circuit connected to a peak detector, and that it turns the amplifier down when a peak is too loud. Let's see how this works in practice. The first two knobs on the Clean pedal are labeled Dynamics and Sensitivity. Dynamics controls what is sometimes referred to as the compression ratio, and sensitivity controls how sensitive the pedal is to quiet sounds. A lot of compressors have a control called threshold, and sensitivity is kind of the inverse of a threshold. If sensitivity is all the way down, then threshold is all the way up, and the pedal won't react, no matter how loud the sound is. As the sensitivity knob goes up, the pedal will react to quieter and quieter sounds. If a sound crosses the sensitivity threshold, then the dynamics knob governs how much compression is applied. If it's all the way down, then the compression ratio is 1:1 and nothing happens. This is an important point. If either dynamics or sensitivity is all the way down, then Clean's compressor is not doing anything. That's not to say that the pedal isn't doing anything, because it actually contains a compressor followed by a limiter, but we'll get to that in a bit. As you turn dynamics up, the compressor will start to act on signals that exceed the threshold set by the sensitivity knob. At about 9 o'clock, it's a 2:1 ratio, which means it's cutting the volume of signals above the threshold in half. As you climb toward noon, you eventually get to a ratio of infinity to 1, which is the same thing as saying that signals can't exceed the sensitivity threshold. An infinite compressor like this is also called a limiter. Now, there's two different designs for limiters, and Clean can be either one. At noon, it's what's called a feedback limiter, and as you sweep toward 3 o'clock, it becomes what's called a feed-forward limiter. The difference between those is that a feedback limiter is keying off the sound after the limiter has acted on it, and the feed-forward keys off of the uncompressed sound before the limiter circuit. This means that feed-forward limiters are faster than feedback limiters and sound more aggressive. Once you get past 3 o'clock, you're in a territory Chase Bliss calls sag. This causes the compressor to push the compressed signal all the way down to the ground, so you only hear parts of the sound that weren't affected by the compressor. Loud sounds become silent, and quiet sounds become loud. Let's try this out. I made a little test harness in Ableton so we can do some experiments. Okay, so what you can see here is that I've got a drum loop, and on the top we can see the uncompressed audio, and on the bottom we have the audio that's coming through the clean pedal. Right now it's turned off. I'm going to turn the sensitivity and the dynamics all the way down, which, as we said before, will mean that the compressor is not doing anything, and I've got wet right about there, which is about a pass-through. And now I'm going to turn this on. Sounds about the same. Now I'm going to turn up the sensitivity, which reduces the threshold, once again having no effect. So now if I turn up dynamics, what we would expect to see happen is for the compressed audio, our lower waveform to be reduced in volume. And that is what we see here. So now if I were to raise the wet gain, which is sometimes referred to as makeup gain, to approximately what it was before, now you can see that it sounds a little different. And also if you look at the waveform, you can see that the body of the notes is much stronger relative to the transient. I'm going to turn it off. Now if we turn it back on, we can hear a lot more of the room sound from the reverb in the room for the drums. So both for the snare drum and for the kick drum. So there's way more body in that snare drum there. Now if we want to, we can increase the amount of, increase the ratio. So now we're at a limiter. And so now what we hear here is that the body is much louder relative to the transient than it was before. No compression. Lots of compression. So this is right now, this is the feedback limiter. Now I'm going to push it to the feed forward limiter. And I'm going to turn the sensitivity down a little bit. So that's that more aggressive limiting that we talked about before. Now, an important thing to look at on this pedal is there's an indicator here, which is this red light. And that shows us when the compressor is actually affecting the signal. So if I turn this to all the way down, no red light, even though the transients are crossing the threshold. If I were to turn this all the way down and turn the dynamics up, once again, there's nothing. But since I just turned the sensitivity up a little bit, now you can see that at the moments that it's compressing the signal, there's a little bit of a red flash there. And that can tell us, it can give us a lot of information about when the compressor is doing its work, and that can help us design our knobs so that they're doing the things that we want. So right now it's doing a lot of limiting on only the top of the signal, and that sounds like this. And if we look at the waveforms, we can see that we're getting just a little bit more body in, right? And another way we could do something similar is we turn this back to here, turn the sensitivity way up, and then so now we got a much softer compression, it's doing less to more of the signal. So this is a smoother and softer compression. So we turn it up. This is a lot more of what you might call a transparent compression. Turn it off. Turn it back on. That's a really subtle difference. Now I'm going to turn this back down, go back up to limiting. Now I'm going to push it past the feed forward limiter all the way into what we call sag. So now the compressed signal is being squashed all the way down, and we are only hearing the reverb tail. Now, something that you're going to notice right away is that we're still hearing the very beginnings of each of the notes. Even if we turn the sensitivity way up and the dynamics all the way down, we're still getting the transients in the beginning of the signal, and that has to do with the attack time, and that's what we're going to talk about next. From the very first compressor available, which was apparently the Western Electric 110A program amplifier, pictured here, compressors have always had some version of attack and release times. From the instructions for the 110A, as the overall frequency characteristics should be flat within narrow limits from 30 to 10,000 cycles, it is necessary to prevent the variable loss network from following the cyclic variation in level at low frequencies. Too rapid insertion or removal of loss would also give an unpleasant effect on peaks of very short duration. If I am interpreting that right, the 110A included attack and release times because if you tried to compress something that had low frequency content in it, you could hear it snapping on and off again as those long waves went above and below the threshold. Additionally, if you had a short transient that only beat the threshold for a short moment, you didn't want to hear the compressor snapping on and off every time something crosses the threshold. So they settled on a 20 millisecond attack and a 250 millisecond release, or if you preferred, you could switch it to a 10 millisecond attack and a 125 millisecond release. Over time, audio engineers came to realize that having control over attack and release times gives a lot of control over the shape of a sound, thus it's more typical now for there to be some kind of more granular control over attack and release times. But the first thing to know about it is the compressor doesn't turn on instantaneously. Its fastest attack time is 0.5 milliseconds. The attack starts when a transient exceeds the threshold set by the sensitivity knob, which means that by necessity, it will not compress the very first instant that crosses the threshold. Now, some compressors have what's called a look-ahead time, where it preloads a few milliseconds of audio into the compressor network to check it out before the compressor kicks in, essentially allowing a compressor to look forward in time at the expense of a little latency. Clean does not have that. As a result, at extreme compression settings, you're going to see the beginnings of transients escaping the compressor. This is normal. 0.5 milliseconds is extremely fast, but it's not time travel into the future. The existence of sag actually lets us really hear how the attack and release knobs behave. Let's jump back into that test harness so we can see what I mean. All right, we're back with our test harness. So let's get back into that sagging territory. I'm going to turn this there. We are all the way in sag. We are only hearing wet. So if you cue back to the middle here. So it's very strangled off, right? Now, if I were to increase the attack, knowing what we know now about the attack phase of the compressor, what we would expect to hear is that transient that is escaping the compressor to get longer. And that's what we're hearing. So this is a slow attack, fast release on sag. Now, something that I've found that's kind of interesting here is that what you're getting now is sort of a boost to the transient of your drums, and also it's sort of a slap back reverb sound. So if you were to bring the dry sound back in, So this is completely dry. So listen to the snare. There's no like slap back reverb, but if I add it back on, there's sort of a slap backy kind of groovy return to the snare sound, which is really interesting and something that is possible because of sag. So that's the attack. So now that I got that back turned off, now there are, it appears to be 3 release settings, but there's actually, there's a very fast release setting, which I believe is 50 milliseconds, and a very slow release setting, which is, I believe, 1.5 seconds, which would be for like a glue compression of an entire mix. You can also set the middle one, which is a user configurable setting by holding down both buttons. And then you can sweep the attack knob, which I am currently actually controlling the release. So this is sort of tailor-made for getting a strong attack and then a nice return to the room sound. So if we were to blend the dry back in there. Turn it off. Normal sound. So that sounds just huge. So you can really dig in and get exactly the drum sound you're hoping for if you want to use Clean on drums in this fashion. So you can, the amount of transient that you want to blend through, you control with the attack, and then you can sweep the release by doing this guy here. If you want to hear what it's doing, I can just turn dry all the way down. So you can hear that slapback sound really coming through. So that is a way that you can use sag to explore what's really happening with the attack and the release phase of the compressor's attack time and release time. And sag is an example of what I'm talking about when I assert that compression is how Clean does what it does, but a compressor is not what it's meant to be, or at least that's not all that it's meant to be, and that's not why they built the pedal. If you go back to the video entitled The Story of Clean, which I watched, 20 times while researching this video, they reiterate something that is right on the first page of the manual but is easy to forget. The idea behind this pedal is to make clean guitar as fun as overdriven guitar. Can clean be as fun as dirty? It's tempting, because clean is a compressor and it's called clean, to assume that the reason it's called that is that it's a nice transparent compressor. That's not what it is. Remember that the original purpose of a compressor was to help hold things into a certain dynamic range. Clean is an analog dynamics processor that was built to see what other kinds of things that kind of circuit could do in addition to compression. As in, well, if we've got a signal caught in this zone where we've analyzed how loud it is and now we want to do something to it, one thing we could do is make it quieter, but why stop there? So sag is the first thing. What if, instead of compressing the signal per se, what if the circuit flipped the dynamics of the signal upside down such that loud things become quiet and quiet things become loud? Is that useful? For what? We already saw one cool use case for that, adding some juice to a drum bus. What are some other things to try? What about an electric piano? Okay, so I've got an electric piano loop here, and you can see that I've got a couple of different things happening in here just so I can show off how a sag can do some interesting things with this electric piano part. Currently, the clean is not turned on. Notice that I've got the attack set here, so fast, but not super fast. I've got the dynamic set to sag. I've got sensitivity set about 10 o'clock. And releases at the fast setting. Okay, let's see what clean will do to this sound. So we got, now what we got is the initial attack turns into sort of a trancey gate kind of situation. The long chords turn into a swelling pad, and then there's a little noodly patch that does not exceed the threshold, so it gets to play on its own thing. So basically, we've turned this single electric piano loop into what sounds like 3 separate instruments, especially if I turn on some delay, which would sound great with this. So I'm going to turn that on. Now on that one. Where's it at? So once again, here's the dry sound. Still going through the delay. With clean. A natural thing to want after you hear sag making those nice swelling pads is, wow, I wish I could make those swelling pads without that plosive transient at the beginning. Well, you're in luck because Clean also has a feature called Swell, which is activated with the left foot switch. When the left foot switch is engaged, that essentially makes the audio signal silent until something crosses the sensitivity threshold. When something does cross the sensitivity threshold, that triggers a special amplifier envelope with its own attack and release time. By default, the left foot switch is a momentary switch, which means it's engaged while you hold it down and then it disengages when you let it go. I find that kind of hard to work with, so I leave the latch dip switch engaged, which turns the left foot switch back into a regular toggle. You can set the attack time and release time by holding both switches and turning the wet knob for the swell attack time and the dry knob for the swell release time. I find that around noon for both creates a nice swelling pad effect, but it probably depends on the tempo of what you're trying to do. The next thing after sag and swell is physics. Once again, our question is, if we start with the idea that this is a processor that does stuff based on dynamics, what's something it could do besides just turning loud things down? What physics does is, by electrically modeling the behavior of a bouncing spring, it destabilizes the amount of compression that's being applied. There are 3 modes. The middle mode, which is nothing, the left mode, which models a wobbling motion, and the right side, which the manual describes as quote-unquote twitchy. I like to imagine the right mode as what happens after you stretch a spring out and let it snap back, versus the left mode, which is what happens when you push a spring to one side and let it wobble back and forth. Physics sounds absolutely sick on drum loops, and it also has a really interesting effect on long reverb tails on things like synths. To me, it mimics the sound of a reverb in a complicated physical space like a stadium or a real canyon, where if you hear a loud noise, it reverberates, but the reverberations also get broken up by the irregular environment. Of course, Clean is a guitar pedal, and in my opinion, the physics are a natural pairing with surf guitar. If you've got some experience with digital audio, something you may have just noticed in that last section is that I just plugged in 3 different sound sources and they all had a pretty nice full signal relative to the available headroom without going over. I did not do a bunch of messing around with levels to make that happen. You would expect that mixing wet signals with dry signals as I was doing and really cranking it up like I was doing, it would have exceeded full scale and clipped my audio input, and that did not happen. Additionally, my guitar, which was clean before I pushed it through the clean pedal, certainly had some overdriven sounds baked into it after the pedal did its work. To understand why that is, let's look at the signal flow diagram from the manual. Audio comes in on the left, there's a signal follower that informs a control center that then goes on to inform the compressor, amongst other things. Then it gets mixed with the dry signal, and then before it makes its way out of the pedal, it goes through another limiter. Clean is what the manual refers to as a 2-stage compressor. The first stage is the compressor with all the controls that we've been talking about. The second stage is a limiter that sits at the end of the compressor network and basically stops you from messing up. You can add an unlimited amount of gain to the front of the pedal and it will not exceed the limiter's threshold at the output. Now, that's not to say that you can add an unlimited amount of gain without coloring the sound. The limiter design is actually a clipping circuit, so if you drive it hard enough, it will start to distort. That may be what you want, though. This is my response to people who say that Clean isn't good for beefing up drums because its attack isn't fast enough. It can seem that way if you try to use the first stage as a limiter. I'll show you what I mean. If you try to compress a drum loop with Clean with the goal of beefing it up, the natural way to try to do it is to set the sensitivity to capture the transients and then move up the dynamics until the transients are tamped down relative to the body of the notes. That will not give you the outcome that you want because the first stage compressor's attack is not fast enough. You will get these snappy transients at the beginning of every note, which is not what you were trying to achieve. If what you're trying to do is beef up drums, the move is actually to engage the second stage limiter by pushing the dry signal. This will give you all the body you could want, and then it leaves you to use the first stage compressor as a transient designer. Get all the beef you want by pushing the dry signal, and then turn dry all the way down, and then you can get whatever transient you want by pushing and pulling the sensitivity, dynamics, attack, and release. Then you can mix the wet and dry signals together and get the best of both worlds. Now, as before, the limiter is a clipping circuit, so it is not transparent as it does that work. It does add some harmonics as it clips the sound. That is just the sound of this device when you use it in this fashion. Since we know that the limiter is a clipping circuit, and we know we can get overdriven sounds by driving it too hard past its threshold, what if we could lower that threshold so that we could make the clipping happen more and get more overdrive? That is what the Dusty dip switch does. It brings the clipping circuit way down into distortion territory and turns the sensitivity knob into a threshold selector. Dusty turns Clean into a sort of fuzzy overdrive pedal with a really distinctive sound. If you mess with the settings and go into sag on the dynamics, you can also get a kind of booming distortion that's really just very cool sounding. And yes, you can blend Dusty mode with Swell mode. Okay, there's one more knob on this pedal, the EQ knob. It has 3 different modes. The first mode, which is in the middle position, is manual mode. In this position, the EQ knob just attenuates high frequencies if you turn it counterclockwise, and attenuates low frequencies when you turn it clockwise. At noon, it does nothing. The manual mode is useful in 2 ways. Number 1 is that it can just be a very convenient way to help situate a sound in your mix after you compress it. The second is that, since the EQ only affects the wet signal and not the dry signal, you can use it to mix some frequencies louder than others. Say you want to just add some low end to a kick drum. Use the manual EQ to remove all the high frequencies and then blend it in. The mixer and limiter do all the work in this case. You don't even need to engage the first stage compressor. The left mode is called shifty. When in this mode, the EQ shifts to the full frequency when the signal crosses the threshold and then shifts back to the knob setting as the compressor disengages. This ends up sounding like a filter attached to an envelope follower governed by the attack and release controls. The best sound I've gotten out of this is a harmonic swell effect, which is a little different from the left foot switch swell because the shape of it is very drastically altered by the relationship between the signal and the compressor, so it feels more interactive. The right mode is a modulated EQ. It attaches the EQ to a low-frequency oscillator which is rotating at a frequency governed by the attack knob. The result is a harmonic tremolo that sounds really great and which I actually think is low-key one of the best things about this pedal. Judging by Chase Bliss's marketing videos and by conversations with other Clean users, I feel like this video went on the journey that most Clean users go on. You start trying to use Clean as a compressor, then you start playing with all the other dynamic options, then you fall in love with Dusty, and finally you're like, honestly, I really like this as a tremolo pedal. If you want a more interactive feeling version of the tremolo, alternatively you can leave the EQ on manual and turn on the motion dip switch. That attaches the LFO to the compressor response so that it destabilizes it in the same way that physics does, but with a repeating oscillation at a frequency that you choose. Of course, you can always mix and match motion with physics and the EQ modes and sag and Dusty in whatever combinations make you happy. There are a bunch of additional options. The only other one I want to touch on is spread, which is an option on all the Chase Bliss stereo pedals. That option adds some stereo movement to the other various options. On Clean it sounds particularly nice on Swell and especially on the EQ and motion-based tremolos. Okay, that's pretty much everything I wanted to cover talking about how the Clean pedal works. Before I wrap up, I mentioned at the beginning that Clean has changed some things about how I play music, and I want to talk about that for a sec. Chase Bliss said they set out to ask the question whether they could make clean guitar as fun as dirty guitar. To me, the answer is an unqualified yes, because when I have my guitar plugged in through my Clean pedal, I get excited about playing clean guitar. Ordinarily, when I'm just blissing out by myself, I'm either playing with synths or I'm playing an acoustic guitar, but when Clean's hooked up, clean electric guitar is my favorite instrument right now. In addition, it's changing the kinds of things that I like to play. There's something about the way that the physics and motion react to your playing that makes me want to try different stuff. In particular, it's gotten me to start trying two-hand tapping stuff on clean guitar, which I'm not very good at yet, but I feel motivated to practice it because when I do it well, I get rewarded with a little tremolo as a treat. Well, thanks for going on this compressor journey with me. Hopefully, if you were a Clean user, you got some use out of this video, or if you're like me and you didn't know a lot about compressors generally, maybe the history stuff was interesting too. Have a great day, everybody.